All right. Good morning, everyone. For folks in the room, thanks for finding us after there was a room change last night. Everyone joining online, thanks for joining this as well. Thanks for your interest in driving enterprise performance with Azure Database for Postgres. Cloud database performance, it's a complex topic. And if you get it wrong, you pay. Ultimately, your monthly bill goes up if you're not making the best use of resources. So it's a really important topic to know what's available. I'm Guy, and this is Denzel. We're in the Postgres on Azure product team. It's a good time to be talking about performance because we have a lot of really exciting enhancements and announcements that we want to talk about. In fact, there is a lot of content in this session, so we will be moving fairly quickly, well, very quickly, so I apologize in advance for that. Here's a brief look at the agenda. So in the next 43 minutes, we're going to start with just what do we even mean by enterprise performance. Then we're going to divide into we're going to split performance problem into three main areas. Scaling up performance, so with a single instance of a database instance, how much can you scale up the available resources and hardware? Then we'll talk about horizontal scaling, how you can scale out for multi-tenant workloads. And then we will finish with built-in optimization tools, how you can take some of the really hard work out of performance tuning for a specific instance. So what kind of, we've got some very interesting autonomic performance improvement announcements and things happening this week. So that's basically the flow of this session. So we'll start then, what do we mean by enterprise performance? I like to define it as getting the maximum performance from the available infrastructure, but without compromising mission-critical demands. So you've got kind of mission-critical pillars like high availability, disaster recovery, scalability, security. So you need to get that performance, but without kind of letting any of these things go. You need to keep that focus on all of these if you're going to bet your enterprise workload on it. So that's kind of the problem space that we're going to be tackling. But it's also worth thinking that Postgres, at its heart, it's a database for developers. So we absolutely can't lose sight of that developer experience. So things like ecosystem integration. How well do we connect with something like Azure Data Factory or Power BI or Excel or your IDE, VS Code? We've got to think about all of those things and focus resources on making that a good experience. And similarly, intuitive SDKs. Let's say you're a Python programmer, then you're going to want the SDK to function like a Python, like a Python programmer needs. You don't want to have it function like an Azure person thought of. So we've got to kind of think of intuitive SDKs. It's important with Postgres to contribute to the open source community. So we have a lot of full-time committers contributing to open source Postgres. And we're also contributing to open source extensions as well. So things like Citus, which you'll be hearing more about today, or things like PG Bouncer, to optimize connection performance. So these are areas that we focus on as well. And then, of course, generative AI apps. Making sure it's not just a good experience and easy to create generative AI apps, but making sure they can work in production. This week, we released a solution accelerator for GraphRag. There's a link to it at the end of this session. That's a good example of how do you get this stuff working in production. There's also labs running every day this week on using AI with Postgres. And having gone through it myself, I really highly recommend that lab. And again, we've got a link to that. So for enterprise, the enterprise database then, let's just dig in. What do we mean by kind of doing work for those mission-critical pillars? So what you see here is an example of features that we've just delivered in the last year. So features around building a secure, like a security perimeter. Something like, I'm not going to go through every one of these, but something like Entra ID support, for example. There, you can centrally manage your authentication. So then you have a security perimeter that you don't get with any other cloud Postgres service. So things like that we really focus on. And the household names you see here, like UBS, Boeing, FedEx, BMW, they're willing to bet their enterprise workloads on Postgres Flexible Server. So we take this very seriously. So that's kind of the space that we're working in. So now I'll get to some of the just a couple of announcements that we've made this week, which are, I'd say, tangential to performance, but very important. So one of these, support for Postgres version 17. If you were at the open source databases session at 8:30, that was a good dive into performance features, including demos in PG17. So I highly recommend, if you missed it, looking at the recording for that. So therefore, I'm not going to spend time on Postgres 17 in this session, but it's worth looking at the key features. I added some of the performance-specific ones at the top of this list here, and I would almost call it a performance release. Things like the more efficient vacuum process. The auto vacuum can now use up to 20 times less memory. So that's a huge difference, and it can really make a difference for a workload. Streaming I/O performance, for example, and then a huge set of performance improvements in query processing. So things like faster correlated subqueries. So overall, I think we published a blog on the Azure Postgres blog detailing the performance features in PG17 as well. So definitely worth looking at. We're listing it as public preview, but if you're deploying like a new server, then you get production support. It's production ready. So if you are like deploying a new workload or a project, definitely take a look at PG17. It could really make a difference, particularly in areas like query processing. One more related feature, you may notice in Azure Portal this week that a new little button shows up when you go into backup and restore, which is backup now. If you're making a change, maybe you've done some performance tuning and you're making a major change to your database service, maybe you want to take a backup right there to get a baseline. This is something customers have been asking us for a long time. We have automated backups every day, but now you can take a backup whenever you want. And if you want to delete it, you can delete it to save storage costs when you're done with it. So this is a really useful feature, and it should start showing up in most of your regions right now. And this is particularly for the general purpose SKU and the memory optimized SKU, which we'll talk about now. So that's just a couple of announcements out the way. Now we're going to really focus on that first section then of scaling up performance. When you deploy Postgres, you get a choice of 3 SKUs to choose from. So for development and testing, you get a low-cost option, which is burstable. And then for general purpose and memory optimized, what's really different between these two is the ratio of vCores to memory. So you get 1:4 with general purpose, and then you get 1:8 with memory optimized. So you can choose which of these SKUs fits your workload the best, based on its demands. And then within each of these SKUs, you get a big choice of effectively VM size and storage size that you can choose from. So with that in mind, and probably one thing worth mentioning as well, it is very easy to switch between SKUs. So you can use this to save cost. You get very minimum downtime when you do this. And then, of course, you've got things like reserved capacity that you can take advantage of to save on cost. So one thing that's in public preview right now is the Premium SSD V2 storage. It's actually been in public preview. It's already in public preview, but one thing that was announced this week is that you can now go from SSD V1 to SSD V2 with just seconds of downtime. What's nice about SSD V2, you get up to 64 terabytes of storage. You can grow this from wherever you start without any downtime. You get 80K IOPS, which is an increase from SSD V1, which is 20K IOPS. And with this, there's also 45% less latency. And when we've done benchmark tests on this, we've seen 4.5 times higher throughput. So again, if you've got demands for high IOPS, it's really useful. But we do have customers that demand more than 80K IOPS, particularly if, let's say, you have a really read-intensive workload and you want more. Well, we have customers using Premium SSD V2 to get up to 480K IOPS. And the way they do this is to take advantage of a Postgres feature called read replicas. So you can effectively spin off copies of your database server, which then can replicate across, like in region to different availability zones, or even you get extra resiliency by doing geo-replication. So if you were to use SSD V2 for all of these read replicas, and then spread out your reads across these, you can have up to 5 replicas. So that's effectively then six machines that you can get 80K IOPS with. So we do have customers right now who are getting 480K IOPS with this type of configuration. So it's an example of, I guess, scaling up and scaling out to get really high IOPS. One other thing I'll mention about scaling up, coming very soon, you will see this very soon, is support for the Intel V6 compute SKU. So this is using the 5th gen Intel Xeon. Now you can get up to 192 vCores, up to 1.8 terabytes of memory. And then per vCore, it's about 17% faster than V5. And one thing that we will do when we support Intel V6 is make sure reserve capacity is available on day one, so you can save costs with this. So look out for this coming very soon. So that's really vertical scaling, scaling up. I'm now going to move to the topic of horizontal scaling. What if you have big multi-tenant workload, you want to scale out your resources? And this is one of my favorite announcements of Ignite, and I'm going to hand over to Denzel to take us through it.
Thank you, Guy. I appreciate it. And I'm going to hang out behind the desk because there are a lot of demos. So we are announcing the Elastic Clusters public preview, which enables workloads. Guy talked about read scale, but this allows horizontal scaling of both reads and writes, and cluster management like tenant isolation, rebalancing of a cluster, ability to start with one node and go on. So, I mean, with the V6 announcement of Intel that Guy made, which is coming soon, you can go up to 192 vCores and 5 read replicas. But that's just read scale. Elastic Cluster gives you an opportunity to scale out. So it takes a host of flexible servers and puts them as nodes in a cluster. And this cluster has a single endpoint the application talks to. You can add nodes to scale out and rebalance the data across them. Effectively, it's a shared nothing architecture. And it's powered by the Citus extension. So Citus is an open source extension that we contribute to and we own. And so this is powered by Citus. So how does this look like? Like I said, the nodes are uniform in the cluster in terms of size. You can start with the node, add nodes as needed. Each node actually has metadata tables that keep track of one database is distributed across this cluster, so keeps track of what pieces of a table are distributed across these nodes. The data itself is broken into shards. And think of shards as a unit of placement, and it's a piece of a table and a unit of placement between the nodes, right? So a horizontally distributed table is broken down into pieces or chunks and shards. And these shards are placed on nodes based on some policy of availability of resources, right? And then a node is designated in this cluster as a coordinator role. There is no dedicated coordinator like some of the distributed database systems. This is a role within a node. And this coordinator role is required to create things like DDL, to create the distributed table, and a few other cluster-wide operations, right? So that's the thing. And at the end of the day, this has a single endpoint that you can connect to. So adding nodes and such doesn't change the application from that perspective. So 2 ways to connect to the cluster. One is using the Postgres default port, 5432. This always lands you on the coordinator node. And so it's, if you're doing a create table or create distributed table, this is the port to use for DDL and schema changes. The other way is to connect with the port 7432. And this 7432 load balances all your requests across all the nodes. So incoming any of the DML requests, inserts, deletes, updates, get load balanced with a 5-tuple hash, and you can query from any node. This eliminates any coordinator bottleneck, if you will, by distributing queries across the nodes. So let's look at a provisioning demo. How do you actually create this Elastic Cluster? It's just a flexible server deployment. So the provisioning experience is very similar. You choose your name, and then where you configure the server, you have a choice of choosing Elastic Cluster, and specifying the number of nodes, and then choosing your compute type. Guy talked about general purpose or memory optimized, as well as choosing your storage type, which determines the size and the IOPS and things of that nature. In addition, you can choose whether you want HA, same zone, or multi-zone, and then create the resource. So it's as simple as that. And you get the cluster, and the way you identify it is you'll see in the overview blade as sharding as schema as row, and the node count, and the availability properties. It's just the normal UI that you see in the portal for flexible server. So let's talk about table types. Now, there are different types of tables you can create in this distributed database. The first being a distributed table. The syntax is create distributed table. This distributes a table between all these nodes and collocates tables that are distributed by the same key. So let's take campaigns table. If we create a distributed table called campaigns, you go to the coordinator node, which creates that metadata for the campaigns table, and then creates local campaign tables for the shards in node 1, node 2, node 3, and distributes them by the distribution key, which in this case is company ID. Right? Similarly, if you create a second table called ads, the same thing happens. The other type of table is called a reference table. A reference table, think of it as a lookup table. So it's a copy of the same table on all the nodes. That table by itself is not distributed, but it's copied to all the nodes. So when you do a join with that table, it's all local. It doesn't have to go through to any other piece of the system, if you will. And create reference table is the way you do that, which makes a copy of that table on all the nodes. And then within a node, of course, foreign key references are maintained. And if two tables are distributed by the same distribution key, they're collocated on the same node. So the join is local. Right? So that's table types. Next, let's look at row-based sharding. So sharding is a process of splitting a table into pieces called shards, which are distributed across the cluster. It requires a distribution key. So if we consider this companies table and the campaigns table, the highlighted column company ID is the shard key. And if you create a distributed table like that, as you insert the data, the company ID is hashed and placed into a shard. And each shard has a range of hash values that can contain it. So it's distributed across the cluster. Similarly, the campaigns table, if it's distributed by the same keys, collocated with the same values of the companies. Right? Now, your queries need to have this distribution key in the query, so in the where clause, in order to isolate it to a particular shard so it's not doing a cross-cluster query. Right? So that's that. Let's look at how we create these now in a quick demo. So I'm showing you a create tables script here. This is just normal tables. You have a companies table with an ID primary key. You have a campaigns table with a campaign ID referencing the company ID with a primary key that includes the company ID distribution key, because that's what we're going to distribute it on. And so, we'll create this, table. And this is not a distributed table at this point. It's just a normal Postgres table. And then we'll distribute these set of tables. And the way you do that is create distributed table. You give the table name, and you give the distribution key. Right? This determines kind of the collocation of all the tables as well, right? And so we execute the distributed tables, and now they're distributed across the cluster. And we'll copy some data into that to see how they're placed in shards. So I copy this data across the cluster. The next table I'm going to create is a GeoIPs. Think of it as a lookout table. I create some indexes. I create a table. And then in here, I'm going to create this as a reference table, which means this table will be copied to all nodes. Right? So let's look at the metadata. We'll copy some data into it. And now let's look at the metadata of the cluster itself. pgdist nodes has cluster-level metadata. You see that this is a two-node cluster. The node name shows the same IP, but the port distinguishes kind of the nodes in the cluster. And the Citus tables table includes all your distributed tables. You see ads, campaigns, and all those as distributed tables, and the GeoIPs as a reference table. And you see for the distributed tables, you can check the distribution column out and see that they're collocated because they're on the same key. The shard count by default is 32, but you can change that on a cluster, right? If you look at distribution across nodes, you'll see the shard is a unit of placement and is placed on particular nodes. You see shards on both 7000 and 7001 port. And if I aggregate this across the nodes, you see that the table is evenly distributed across both nodes. This is a small table, but it's evenly distributed as data was ingested, right? There's nothing you have to do from that perspective. So the next thing we'll look at is schema-based sharding, right? So row-based sharding, of course, you need some amount of schema changes because you have to kind of choose a distribution key, and your queries have to have that predicate and so on and so forth. In schema-based sharding, there's no query or schema changes required, right? The schema itself is how things are distributed. So you can have a different schema per tenant also if you have a multi-tenant applications. It's the easiest to really port. So if you consider a multi-tenant application, for example, which is a retail application, has products, product orders, details, and you sell this application to multiple customers, you can have a schema per tenant, and that schema will be distributed across the nodes. So schema for tenant 1 may be on node 1, schema for tenant 5 might be on node 2 based on kind of the placement constraints, right? And then effectively, to access it, your application just has to set the search path to the schema and access the tables just like normal. So it's easy if you had a database per tenant applications to port to this scheme too. The other use case is using it for microservices. If you have microservices-based app, you can have a schema per microservice and collocate all these databases on a cluster. So you can isolate microservices that are large and so on and so forth. So let's look at the first retail type application that we talked about. If you have products and inventories and you have a bunch of tenants, let's look at how that would be created. So I create a schema called Contoso. Let's say I start on an actual Postgres instance. It's not a distributed schema. I have the products table, I have an orders table, and I have an orders detail table. So I create these three as schema. At this point, it is not a distributed schema because I've not done anything to distribute it. So if I look at Citus schemas, actually, I'm going to load some data first. And so this is an existing table which is not distributed. If I look at Citus schemas, it's going to give you 0 rows because this is not distributed, right? The way you distribute it is to call this Citus schema distribute. This distributes the schema and copies an existing table to a distributed table too, right? So if you have an existing schema that you want to convert, that's the way to go. And you see now that this appears in the metadata as a distributed schema. And if you look at Citus tables, that same Citus table type shows schema as the distribution type, right? It's not distributed table, it's a schema sharding, right? You see the table size, you see collocated. All the tables in that same schema are collocated in one place, right? So similarly, if you look at shards, you'll see that the shards all belong to one node because they're collocated. So you see the node port orders, details, all have the same collocation ID and belong to the same node because the node port is 7000, right? So to make it easier, there's a configuration, enable schema-based sharding to on. If you turn this GUC on, then any schema you create is now a distributed schema. You don't have to actually do the whole create distributed schema. So your application, if it creates a schema per tenant, it'll automatically create a distributed schema, right? So we're going to take the same set of tables. We created another customer called AdventureWorks and one called Wide World Importers, and we loaded the same data that we had before. If you look at Citus tables, we'll see the tables for all these three customers, right? And each of the schemas are collocated, right? Tables within each of the schemas are collocated, right? So because that's the way data is distributed. Similarly, looking at Citus shards, you'll see the schemas placed on one node. And of course, not every schema is placed on its own node because maybe the space constraints or the are still relevant. You can still fit multiple schemas within the same node, but they're co-located from that perspective. Okay, So what sharding model do I use? Schema-based sharding, as we've seen, no schema changes are required, right? No changes to query. You don't need the predicate to have a tenant ID or anything of that sort. If you want lower density, there's an impact for Postgres to have too many schemas, right? So if your number of tenants is in the low thousands, it's fine. If you're crossing a threshold, there's overhead to maintaining the number of schemas in Postgres. But there is ability to actually, it's easy to lift and shift existing database per tenant apps, and there's an ability to isolate schemas on a particular node and things of that nature. On the other hand, row-based sharding can have really a high density of customers, right? One more thing on the left is a schema provides more of isolation of tables for a tenant, right? On row-based sharding, you can have a high density of customers, greater than 100K tenants. Of course, you need to do some work in terms of potential schema changes and sharding keys, including that in primary keys of related tables so that they're co-located. Security can be done via row-level security here. And you can still isolate tenants and move shards around. The cluster set of functionality still apply, right? So let's talk about queries across the cluster. The goal of the Citus extension is actually to make a distributed table look like pretty much a regular table, right? Postgres has hooks that you can hook into, whether it's planner or executor or utility hooks, that the extension actually hooks into and invokes the distributed planner if a distributed table is actually invoked, right? So it uses utility hooks for DDL, for things like copy or create table. It uses planner hooks for distributed planner for queries that need to go cross-node. So let's take this simple example of a query. You have an average spend across a campaigns table, so it hits all shards. There's not a predicate actually associated with it. So this, goes to the node that it goes to, wherever you connect. And, there are tasks that the query is broken into that are pushed down, and parts of the query could be pushed down. The entire query could be pushed down by the distributed planner. And then data is fetched from those, other nodes if required, aggregated on the node the query begins on, and then sent to the client, right? So that's at a nutshell. So let's look at few examples of types of queries, right? So you have, select star from A, where A.key equal to 3. This is your partitioning key, distribution key. If that is the case, if you connect to the cluster, if you land on a node that has that data, that's the only node shard that it's going to hit and return that one row, right? You could land on a node that doesn't have that data, in which case it would go to the node that has that data, but it's one hop. It's localized to kind of that one node, right? Because you have the where A.key equal to 3, we can know which shard has that data. Similarly, what if you have a join? You have inner join A, inner join B on the key with a predicate. Kind of the same thing happens. If the tables are co-located because the distribution key is the same, it'll just hit one node and push down that query to that node. It doesn't go cross node. It's super quick. So what if you don't have a predicate? So you have just the same join that we had before, but we don't have a where clause that isolates it to one shard. In this case, your query originates in one node, but has to hit every shard. But the join is done within each shard, right? Because the tables are co-located. You're not going cross shard and cross node for the join. So those pieces are aggregated from each task and then returned to the query. And the last example, of course, is if you join on any non-partition key. And this is a pattern you want to avoid because it's more expensive. In this case, you start in a node, but to join these two columns, you have to retrieve data from multiple nodes, multiple shards all across the cluster because they're not co-located, necessarily. So that's that. So let's look at some of these examples with query plans in Postgres. Let's take this companies table. And campaigns table. Here we are looking at a company ID 5. I'm going to have that 5 in my predicates and see how that works. One of the columns one of the functions that is there is get distribution column name, which gives you a shard key number. That's 722, 102, 722. And then you can see where that shard belongs to by using cited shards. I have an update that has this very company ID equal to 5. You see it's isolated to the port 7000. It has only one task, and it's hitting the local table, because these are local tables for each shard on that node, and then returns really quickly. And that's because it had the predicate company ID equal to 5, right? In the second question, second query, sorry, I have an inner join on 2 co-located tables, and I have a sum, which is an aggregate. I don't have a where clause, right? In this case, you'll see a bit of a difference. It has to hit all the 32 shards, right? And we have a sample, one of 32 shards plan shown. But the whole, query in terms of the aggregate itself can be pushed down to each shard, right? So you have the join, the scan, and the aggregate, and the sum, all being pushed down to each shard. It's done on each shard and then aggregated and send it back. In the last case, I have group by cost model, which is not a distributed column, right? And I'm doing the same sum of monthly budget. In this case, you see the task count is 32, and it has a local aggregate, which it can push down for the sum on each individual. But the final group by is actually on a non-grouped column, so it has to do a global aggregate, to aggregate kind of what is being sent from each node. So there's a piece around that. So these are 3 patterns. Of course, there are many other patterns. And the plan is going to show you also some new operators that the Citus extension adds. Okay, some workload patterns, high throughput OLTP patterns, multi-tenant applications like we talked about, IoT due to the ability to actually scale out writes and add nodes as you want, real-time analytics and microservices, all of these are this. We're going to look at like one quick pattern and considerations around that called multi-tenant. There are 3 really ways to look at multi-tenant. Customers have a flexible server per tenant, which becomes a problem because you start like having to manage a whole fleet. You can have a database per tenant, which has a metadata application has to deal with metadata on which tenant is in which database and manage that whole process. Or you can have a sharded database, which the application then has to maintain, okay, what tenants are in which database of the system and the whole hassle that goes along with it when it comes to shard splits and shard merge. So that's complicated. Citus or the Elastic Clusters takes that away from you, right? The important considerations of multi-tenant app are cost per tenant. You can have density of packing here with the clusters. Scaling per tenant, you are able to add nodes easily. Tenant isolation we'll talk about soon, and business continuity. We have something called online shard rebalancing, and these are needed in 2 places. A, when you add a new node. If you just add a new node and don't do anything, only new data is going to go to the new node as shards are added, right? Alternatively, you can rebalance the existing data online across all the nodes in your cluster. And that happens when you add a new node or when a node is getting hot, right, for whatever reason. Storage is being maxed out, things of that nature. But this rebalancing is online, and we support shard moves and shard splits. And this is done with logical replication under the covers, right? So that's online rebalancing. And the way it does is it goes on a rebalance strategy. The default rebalance strategy is based on disk size. But there are availability to customize rebalance strategies. It's a function. You have the ability to customize it as you wish from a rebalancing perspective. The next one is tenant isolation. Think of noisy neighbor in a multi-tenant scenario where a tenant grows in importance, right? So he wants his own server. He wants dedicated performance, capacity or whatever else. So this can be used to actually add a new node, for example, and isolate a single tenant to that node, right? Or move other people off this node so that this node is dedicated to this tenant. Again, this is online. No application code change is required or downtime required. Right? So let's look at this real quick. So I have a 2-node cluster here, I'm going to look at these tables. So I have AdventureWorks and Contoso. Contoso has become my important customer. It's on port 7001. So I'm going to, there's another customer, Wide World Importers, also on that same node, if you will. So I need to isolate one of them. So how do I do that? So the way I do that is with Citus schema move. This is for a schema-based sharding example, the same one that we saw before. And so what I'm going to show you on the right is a workload running. It's just an update of a column. And we're going to move this wide world importers off node 7001 so that Contoso is isolated on that. Right? So I execute the statement, and the move has happened, and the workload on the right is still executing. There's no blip, if you will, in that workload. So we talked about a lot of things. There are cluster-level benefits from business continuity to HA to metrics to security to manageability that you get along with this. And the last quick demo I have is to show that this linearly scales, right? I mean, if not, what's the point? So I have 2 clusters here. The top one is a 2-node cluster. The bottom one is a 4-node cluster. Right? And I'm going to run a PG bench. And the PG bench effectively is connecting over this 7432 port -P so that these requests are load balanced across the cluster. Right? And I have tenant queries.sql, which PG bench is generating random tenant IDs and issuing some selects to them. Right? And 256 clients running against each cluster. And we'll see quickly what the difference in 2-node and 4-node is. The latency or average TPS is 123K, 123,000 transactions per second with latency of 2 milliseconds. The latency below for 4-node is 1.2 milliseconds, which is lower at a higher TPS because the previous cluster is more resource bound, right? So I'm looking at metrics. It's almost 100%. This is little closer to 90%. Even at the metrics level, you can split this by cluster name to see what nodes, right? What nodes are consuming resources. So we enable that view of metrics as well. So that's monitoring elastic clusters in a nutshell. The next thing we want to talk about is now we are transitioning to the optimization phase, right? What the service has to help you optimize. We are announcing the general availability of index tuning here. Index tuning is a service that actually looks at your workload, analyzes your workload, and provides index recommendations at a workload level, right? So it allows create index recommendations, drop index recommendations, and we are just enhancing that even more. And we'll see that in the demo. This is based on Query Store being enabled. Query Store, if you're not familiar, tracks all query execution and is a great way to actually even baseline your performance, see when plans change and things of that nature. And the recommendations are not on a per query basis. This uses some MSR algorithms to look at the workload as a whole and optimize index recommendations are based on the tuning set, not just an individual query. So let's quickly look at kind of the demo on this. So to enable this, I mean, literally it's an enable button. We have a set of tuning options, both for create. First, there's a tuning interval, which the default is 12 hours. And you have a set of options for create, which indicate like what how many top N queries you want to do this, and what's your estimated improvement before we should recommend that. And then you have options around drop indexes. Okay, only recommend if it's not used for 30 days, things of that nature, because you don't want end of month reports, for example, to be affected, right? And so that's the enabling experience. So then this runs in the background, so I can't really wait for the hours and run the workload to show this. But the index recommendations look something like this, right? So you get a set of index recommendations, and if you click on each index recommendation, you're going to see a few things. You'll see the index, you'll see the script, you'll see when it was first recommended and last recommended. So if you've created it, you shouldn't recommend it again. You'll see the average improvement and the index size, and then you'll see the queries that it affected, and the reason, right? So this is a rich set of data in terms of evaluating now, should I create that index? Because you know what it'll affect, right? So that's that. So let's look at this from the query store perspective. We have an intelligent performance sessions which tell you what sessions ran, and effectively you can query this too. The index recommendations, and why might you want to query? Say you want to look at a particular query and see, okay, what all indexes affect the query? Because the index recommendations are per workload. You can flip this by querying it and see that angle. So we return a JSON with impact of queries, what's the index recommendation, what queries are affected, and the costs, right? And you can actually flip that to do that. So creating these indexes, this was a TPCH workload. So I created the indexes here, and we'll see the improvement in performance in a second. This was before index creation. CPU was at about 70%, and pretty hot. And then this was after the index creation. There's quite a bit of a drop of performance. This is incredibly helpful because it's not just looking at one query. Query store also is incredibly useful because it can be used to compare baselines. Here I wrote a function to take a baseline time and a comparison time, and I can look at every query with the query hash. I can look at the baseline plan and the comparison plan to see if the query plan changed. I can look at the calls because, of course, if latency is reduced, I can look at the execution time. If latency is reduced, like it is in this case, the number of calls per second will go up, right? And compare performance. So that is index tuning in a nutshell. I will hand it over back to Guy to talk about server parameter tuning.
All right, thank you. I love those demos, Denzel. Thank you. OK, in the 2 minutes that we have left, I'm just going to very quickly introduce a really exciting feature that's coming soon. Denzel went through optimizing index performance tuning. And that's kind of a hard, complex problem space. And so is server parameters. It's really it's a real strength of Postgres that there are hundreds of server parameters, covering all these various areas like connectivity, logging, buffer management, write-ahead log settings, and then there's a whole ton of extension-specific ones. There's usually good defaults, depending on kind of what VM size you pick, things like that. But really tuning specifically for a workload, it can be hard work. It can require a lot of manual effort, a lot of time, and also a lot of specialized knowledge. So that's really what we're addressing with another autonomous tuning feature, which is called server parameter tuning. It's actually coming very soon. It's not quite in public preview yet, but you should see this being announced soon. And the goal here is it doesn't change every server parameter. It picks a subset that are most relevant to workload performance. So you can then start running a workload, and you can start a tuning session. You can start running a workload against it. It will try. It has this AI-powered tuning engine, which will then try different configurations, make inferences, try additional iterations, and gradually build up a profile to identify the best server configuration for this specific workload. It's also really easy to use. So what you will see once this becomes public preview is there'll be a new setting on the left under intelligent performance called autonomous tuning. And there you'll be able to just select enable tuning. And what you'd do at this point is you would start running a workload. So if you've got a particular reference workload that you need to tune for, you start running this workload and you pick run tuning session. Now, some server parameters it modifies will require a server restart, and some won't. So you can choose. If you say no restart, then it will only modify server parameters that don't require a restart. So for example, if this is maybe a system running some important workloads or production workloads, you may not want to restart it. So you can make that decision and then run your tuning session. So what it will do is you'll start seeing these tuning iterations appearing where it will make some changes, it will try them against your workload, and then it will keep going. So it will keep building up, and you'll see various KPIs or various performance indicators like the TPS, the AQR, average query runtime, areas like that. And then you can look at a session and view the CPU, IOPS, IO throughput over time as well. And then once it's been through these iterations, you can then select different tuning sessions or different iterations and pick the one that's best based on the parameters that are most important for you, like average query runtime, or you can go pick a different one, just depending on what's most important. So you can look at all the different stats for these iterations and then just pick the one that works best, not just for your workload, but maybe you want to take other workloads into account and things like that as well. So that's it in a nutshell. I know we're out of time now. Just the key takeaways from this session then. We split up the complex performance problem space into 3 main areas: scaling up with applying larger SKUs, better hardware; scaling out with elastic clusters; and then new methods of taking the hard work, in a sense, democratizing index tuning and server parameter tuning with autonomous logging. So that takes us to the end. We will hang around for questions. I know we used up all our time. We'll hang around either here or out there. So we'd love to chat about any of this. And then there's some useful resources here as well. Some of going deeper into some of the AI topics, there's some good resources. There's our blog that covers all of these topics. And then the other sessions at Ignite. And if you want $50 for 15 minutes, meet some PeerSpot representatives up in the experts hall. And you also get some good swag. If you fill in their survey, you get an Azure Data scarf, which is really cool. So that's all. Thank you very much. Thanks for joining.